5 centimeters. That is the thickness of the material standing between you and a bullet traveling at 900 meters per second. Not steel, not concrete, glass. The same material that shatters when you drop a coffee mug, engineered to absorb the force of a rifle round and stop it completely. But here's what nobody talks about. Bulletproof glass is not actually glass, and the science behind how it works will completely change the way you look at every protected window you have ever seen. In the next 4 minutes, we are going inside the factory where this material is built, layer by layer, and revealing the exact science that turns transparent material into one of the most powerful protective barriers on Earth. Let's start with a question that seems simple but isn't. Why does ordinary glass fail? When a bullet hits a standard glass pane, the impact energy has nowhere to go. The glass is rigid and brittle. It cannot flex. It cannot absorb. It can only crack and shatter in a fraction of a millisecond. The bullet passes straight through, carrying almost all of its original energy with it. So, the engineers asked a completely different question. Instead of trying to make something harder, what if you made something that could absorb and redirect energy without breaking? That question led to one of the most counterintuitive engineering breakthroughs in modern materials science, and it all starts with something you would never expect: plastic. Inside the factory, the process begins not with glass at all, but with polycarbonate, a high-performance thermoplastic polymer with extraordinary energy absorption properties. Polycarbonate on its own can flex under impact without shattering. It bends, absorbs, and recovers in ways that rigid glass never could. But polycarbonate scratches easily, and it has one critical weakness: it cannot stop the initial penetrating force of a high-velocity round on its own. So, the engineers combined it with something it could never be alone. They bonded it permanently to precision-cut panes of optical quality glass using a chemically reactive liquid resin called PVB, polyvinyl butyrol. What happens next inside that factory is where the real science begins, and it is extraordinary. In the next 30 seconds, you will discover why the order of these layers is not just important, it is everything. The glass panes and polycarbonate sheets are cut to exact dimensions using computer-controlled water jet cutters, tolerances of less than 1 millimeter. Each layer is then cleaned in an ultrasonic bath, removing every microscopic dust particle that could create a weak point in the final bond. The layers are then assembled in a cleanroom environment, a sealed space where the air itself is filtered to prevent contamination. The stack looks deceptively simple from the outside, alternating sheets of glass and polycarbonate, each separated by a thin film of PVB resin. But the configuration of those layers, which goes first, how many are used, and at what thickness, determines exactly what threat level the finished panel can withstand. A standard car window protection panel uses 3 layers. The glass in a presidential motorcade uses up to 12. Now, the stack enters the autoclave, a pressurized industrial oven that can reach temperatures of 140 degrees Celsius and pressures of up to 14 bar. Inside the autoclave, something permanent happens. The PVB resin melts and flows into every microscopic gap between the layers, chemically bonding the glass and polycarbonate into one unified structure. When it cools and comes out, it is no longer a stack of separate materials. It's one composite structure, and its behavior under impact is now completely different from any of its individual components. This is the moment where material science becomes something almost magical. What happens next when a bullet actually hits this material is something you have to understand step by step to believe. When a bullet traveling at 900 meters per second strikes the outer glass face, that first glass layer does something that looks like failure. It shatters. But that shattering is engineered. The cracking of that outer glass layer absorbs and disperses a massive portion of the bullet's kinetic energy, spreading it across a wide surface area in microseconds. The bullet is already slower and deformed before it reaches the next layer. The polycarbonate layer then flexes, absorbing and redirecting the remaining energy sideways and outward rather than inward. If there are multiple glass layers behind it, each one repeats the same process, cracking to absorb, slowing the projectile further with every millimeter it travels. By the time the bullet reaches the final polycarbonate backing layer, it has exhausted almost all of its energy. It stops, held inside the material, permanently, never reaching the other side. But here's the detail that almost nobody knows. The threat level system for bulletproof glass goes far beyond what most people imagine. A level 1 protection stops a standard 9mm handgun round. Level 4 stops armor-piercing rifle rounds. Level 8, the classification used in the most extreme applications, is rated to stop multiple direct hits from a .308 caliber high-powered rifle. The glass protecting the most powerful leaders on Earth is not just thicker, it's a completely different engineering solution at every level. Some panels used in head-of-state vehicles weigh over 150 kilograms per square meter. The doors on some armored vehicles are heavier than a small car. And the final innovation in this technology, the one currently being deployed in next-generation applications, takes the concept even further. Researchers have now developed transparent aluminum, a ceramic compound called aluminum oxynitride that is optically clear like glass, but harder than steel. It's currently used in military aircraft sensor windows and classified armored applications. The next generation of protective glass will not be glass at all, and it will make everything we have described today look primitive. Comment below. If you had to choose between armored glass and steel plating on a vehicle you were riding in, which would you trust more, and why?